In this example, we're going to do a hypothesis test given two independent samples. So the first sample comes from a group of non-smokers exposed to tobacco smoke, and then we measure their cotinine levels. And then the second sample comes from a group of non-smokers not exposed to tobacco smoke, and then of course we measure their cotinine levels. So in this video, we're going to use a 10% significance level to test the claim. Let me go ahead and highlight that original claim that non-smokers exposed to tobacco smoke have a higher mean cotinine level than the non-smokers not exposed to tobacco smoke. So we'll do a hypothesis test in this video, and then in the next video, we'll test the claim again by building a confidence interval. So the very first thing that you want to make a note to yourself is that we are interested in looking at mean cotinine levels. So this is a reminder that we're dealing with a population mean. That's the parameter of interest. So I'll write that up at the top. Population mean, which we call mu. So mu represents the mean cotinine level. And since we have two independent samples, those two independent samples come from two separate populations. So let's identify those two populations. The first population, we'll call that the group that is exposed to tobacco. So, I'll write down here, mu1 is the mean cotinine level for the first group, and we'll just say the group that's exposed, meaning exposed to tobacco smoke. And then mu sub 2 represents the mean cotinine level for the population. Cotinine, let me make sure I spell that correctly. All right, for the group that is not exposed. So not exposed. Okay, and then going back to the original claim here, we're testing the claim that the mean level for those exposed is higher than the mean level for those not exposed. So if I write this down using symbols, this is the original claim that we're going to test. And we're saying that mu1, all right, the mean for the group exposed is higher than mu2. So if we take a look at this original claim, we can see that it contains the greater than sign. So I'm going to go ahead and write down the null and alternative hypothesis. So that's the first step in doing a hypothesis test, which is to write down our hypotheses. Okay, so we've got the null and the alternative. And again, because the original claim here does not contain the equal sign, that automatically becomes the alternative hypothesis. Okay, and so then we have to determine what is the null hypothesis. The null hypothesis always contains equality. So the null hypothesis, we always assume that the two mean levels are the same, and then we try to find evidence to either reject that or fail to reject that. So the original claim was the alternative hypothesis. I'm going to keep track of this so that I know how to write my final conclusion at the end. And then also, because the alternative hypothesis contains the greater than sign, I know that I have a right tail test. So a one tail, right tail test. Okay. So now we need to gather some sample data to test the claim that mu1 is greater than mu2. So from the problem, we do have some sample data for each group. So I'll squeeze it in the top here. For the group that is exposed to tobacco, our sample size n sub 1 is 40. Our sample mean, so the mean cotinine level for this sample is 60.58 nanograms per milliliter, with a standard deviation of 138.08 nanograms per milliliter. So that's our first group. And then our second group, the sample size was, let's see here, 45. So n sub 2 is 45. The mean cotinine level for that group, so x bar sub 2 was 16.35 nanograms per milliliter, with a sample standard deviation of 62.53 nanograms per milliliter. So if we just take a look at our sample data, we can see very clearly, I'll highlight this in a different color, green, that the sample mean, okay, so the mean cotinine levels for the two groups is clearly different. So we can see that for the group exposed to tobacco, 60.58 is much higher than 16.35. So it seems to support this claim that the cotinine level is higher for those exposed to tobacco, but we need to know if this difference is statistically significant or not. And we want to make sure that we don't just see the difference because of the sample that we obtained from our two samples. So to do this, we have to go through the hypothesis test and calculate a test statistic for the difference of the two sample means. So that's the second step. We're going to calculate our test statistic. And again, the test statistic here is either going to be a z-score or a t-value, depending on if we're using the normal distribution or the t-distribution. So to figure out if I'm going to use the normal distribution or the t-distribution, we need to go back to the problem and ask ourselves if we know what the population standard deviation is, meaning do we know, so I'll write down here, population standard deviation, sigma. And if we go back to the problem, you can see that sigma is not given to us, so it's unknown. Anytime that sigma is unknown and we don't have sigma, we're always going to use the t-distribution, meaning that we're going to use a t-test to do the hypothesis test, okay? All right, so first thing is, let's go ahead and see what the difference is between the two sample means. So if we do the subtraction, 60.58 minus 16.35, we see that that is a difference of 44.23 nanograms per milliliter. Okay, so it is a positive value, so we expect that the test statistic is going to be on the right tail of the normal or of the t distribution on the right. So I'm going to use the graphing calculator to actually get that test statistic, even though we can also use formulas. But to save time here on the calculator, we're going to use the two sample t-test. Okay, so 2 because we have 2 independent samples, and then t-test because sigma is unknown. Okay, so when you put that into your calculator is going to give you a t-value of, let me see, what is the t-value? 1.863, 1.863, and then I'm going to go ahead and write down the p-value because the calculator will also give you that. So that's typically the third step here. So the p-value is 0.03399. So I'm going to circle these two values in green, and then I'll plot it on the t distribution on the top right here. So a couple of things to remind ourselves is that our significance level is 0.10, and we have a right tail test. So that means that I'm going to shade on the right hand side here. Let me go ahead and mark this 0, 1, 2, 3. So on the right hand side, I'm going to shade in the area that's just a little bit above 1 because the critical value that corresponds with an area of 0.10 on the right hand side. So that's your alpha. That's a critical value of 1.30. So you can use inverse t on your calculator to get that value. So that'll give you t sub 0.10, which is 1.30. Okay, so if we take a look at our test statistic of 1.863, that test statistic tells us that a difference of 44.23 is slightly above 1, slightly below 2, and it's obviously above 1. So I'm going to mark it in green here on this bell-shaped curve. So that right there is your test statistic. And it's the value of 1.863, and that's the test statistic for our x bar sub 1 minus x bar sub 2. So we can see that our test statistic falls in the critical region. So now we can make a conclusion about the null hypothesis. So that's step 4. So here, because our test statistic, so you can say since your test statistic, which is 1.863, falls in the critical region, right? We can reject the null hypothesis, meaning that the difference that we see in our sample data, so the difference in the two cotinine levels, is statistically significant. It's so far away from the center where at the center, this is where mu1 equals mu2. So this is enough for us to say that the mean cotinine levels, mu1, does not equal mu2. Otherwise, our test statistic would be closer to the center. It would be closer to that 0 value. Okay, if you're using the p-value method to make a conclusion about the null hypothesis, then let me shade in the p-value. So back to this bell-shaped curve, What I'm shading in green here, that represents the p-value. Okay, so that's the probability of getting a difference that is at least as significant as the one that we see in our sample data. So that's approximately 0.03399 or approximately 3.399%. So here we can see that the area shaded in green is smaller than the area shaded in red. And what this implies is that the probability of getting the difference in our sample data, right, is very, very small compared to our significance level. So we can say here that since our p-value is less than our significance level, and we can see that 0.03399 is less than 0.10, we would also reject the null hypothesis. So now we can make a final conclusion about the original claim. So because we're rejecting the null hypothesis and the original claim is the alternative hypothesis, we would say that there is sufficient evidence to support the claim that, and I'm running out of space here, but you would just rewrite the claim up at the top here. So you would just rewrite all of that. So we would say there is sufficient evidence to support the claim that non-smokers exposed to tobacco smoke have a higher mean cotinine level than non-smokers not exposed to tobacco smoke. So real quickly here on your calculator to perform that 2-sample t-test, go to Stat, okay, tab over to Tests, scroll down to option 4, 2-sample t-test, okay, put in all the information on your calculator, so it's going to ask you for all your sample data for your 2 samples. Make sure that you choose the correct alternative hypothesis. When it says pull, choose no. And then when you press enter, it's going to give you the, again, I always tell students to double check to make sure you typed in that alternative hypothesis correctly. So double check that with what you wrote on your paper. And then you've got your test statistic, that t-value, your p-value right below it. Okay, and then if you keep scrolling down, it just kind of gives you all the sample data that you typed into your calculator. So you can double check that to make sure that you typed it all in correctly.